There's more homework problems from Chapter 9. Numbers 39 to 45. And these problems are about the conservation of linear momentum. That means what we have discovered, proved via lab activity and also via little theoretical physics action, that the momentum before a collision or explosion or interaction is the same as the momentum after. So the total momentum before, sorry, it's an ugly looking sigma there. The total momentum before something happens is equal to the total momentum after some interaction. And that is a powerful problem-solving tool. So, for example, in 39, we have a man lying on a surface of negligible friction. He shoves a 68-gram stone away from himself, giving it a speed of 4 meters per second. What speed does the man acquire as a result? So here's the beginning. We have man and stone, and they're at rest. So the total initial momentum is 0. And afterwards, the stone's going this way, so the dude is going to have to go this way. Sorry, that's supposed to be straight. Like this. So that means in magnitude these would have to be the same, or they have to add up to 0. Right? So the momentum that he gave the stone, if this is 0, this has to be 0 too, right? Because the total linear momentum is conserved. So the momentum of the stone, which is 68 grams mass times the velocity he gave the stone, 4 meters per second. You think he could have given it a bigger push than that, but whatever. Plus the momentum of the guy, which it's his mass, 91 kilograms. You could have gone on a diet too, that might have helped. But I guess he didn't know he would be in this predicament. And then the velocity of the guy, whatever you want to call that, v, that has to equal 0. And if you're looking at that, well, how could that equal 0? Well, this is going to have to be negative, right? But that makes sense. If we call the velocity of the stone positive, then his velocity would have to be negative. So, let's see. We've got 0.068 times 4 divided by 91. So he acquires a very sad velocity of 0.0030 meters per second. Or if you want to make it sound a little bit more tragic, or maybe more optimistic, I guess, depending on how you look at it, would be -3 millimeters per second. So, moral of that story is, well, I guess it has several morals. Don't get stuck in the middle of a frictionless surface. And if you do, bring a stone with you that has a mass of more than 68 grams. 41, let's see where we're at here. Sorry. Find my place. And pick up my pen. All right, 41. We've got a little configuration of blocks here. They're calling it a two-ended rocket that's initially stationary on a frictionless floor with its center at the origin of an x-axis. The rocket consists of a central block of mass 6 kilograms and 2 blocks on each side, sorry, 1 block on each side, 2 blocks total, with masses of 2. Small explosions can shoot either of the side blocks away from the block C and along the x-axis. Here's the sequence. So at time 0, block L is shot to the left with a speed of 3 meters per second relative to the velocity that the explosion gives the rest of the rocket. Okay, so this is the tricky thing about this. So that means, like, if you were sitting here on top of this block here watching, then after the explosion you would see this thing going away from you at 3 meters per second, but of course you're going this way, so that's a little tricky here. The best way to deal with that, I think, is that the difference in the velocities is 3. So whatever the velocity of this one is after the explosion, let's say that has a velocity of v, then when you add the velocities together, when you subtract the velocities rather, you get 3. So this one would have a velocity of 3 minus v, where v is just the speed of this, right? The positive version of that. So think about that for a second. If this one got shot off in this direction with a velocity of 1, then this one would be going this way at a velocity of 2, because then, according to you here, you're going 2 meters per second this way, and if that's receding from you at 1 meters per second, then that's going to appear like it's moving at 3 meters per second. So that's the tricky thing about this problem. If this one's going this way at v, then that would have to be 3 minus v. That's that relative to business. All right, and then next at time 0.80 seconds, block R is shot to the right with a speed of 3 meters per second relative to the velocity that block C then has. So at t 2.80 seconds, what are the velocity of block C and the position of its center? All right. So that's a little bit complicated. So let's figure out the first part. Let's figure out what those velocities would be. So the initial momentum of the whole system is 0, which means the final momentum will also be 0. So that means the momentum of this has to be equal to the momentum of that, right? They have to cancel each other out. Or you could say their sum has to be 0. If you make their sum equal to 0, you have to recognize that one of these has to be the negative direction. So I think I would call this, you'd have to put a negative sign in front of that. So the total momentum after would be negative 2 times v, that's the momentum of this block, plus 8, these two are still stuck together, times 3 minus v. That would have to be equal to 0. So, looks like a algebra problem here. So it looks like v is going to be 2.4 meters per second. Oh, and that's what the v is, right? That's the velocity of this. So that means that these two moving off to the side now I've got the 6 and the 2. The velocity of those is 0.6 meters per second in this direction, right? 3 minus v. Just be careful that you recognize what you solved for there. Okay, now they're going to cruise for 0.80 seconds. So the distance that they travel in the first phase of this little sequence here, since it's a constant velocity, is just the velocity times the amount of time, which is 0.8 seconds. So that's 0.48 meters. That's what happens in that first bit of time. Okay, now explosion number 2. So block R is shot to the right with a speed of 3 meters per second relative to the velocity that block C then has. Okay, so block C has this velocity now, and afterwards, after the collision, we're going to have the same kind of situation. This block is going to have a velocity. I'm going to call that v. And then this one is going to have a velocity Well, we don't really know what direction it would be going in. That's a little bit tricky, isn't it? Because it could, depending on how big the explosion is, this is a bigger block, right? So it could remain going in this direction or could go in the other direction. So that's a little bit tricky. So let's say that this one is still going, well, let's say we assumed that it was going to go the other way. I think that that's probably wrong, but that's what you might initially assume because of this. So then, same deal, if this one had a velocity of like 5 going in this direction, or a speed, I should say, then this one would have a speed of 2, or in other words, v minus 3 in that direction, right? 3 less than that. Is that right? No, that's not right, is it? Because if this one was going in this direction with a speed of 5, this one would have to be going in that direction with a speed of 2, right? For the difference to only be 3. So I think it's going to be the same thing, right? If that one had a velocity of, let's say, 2 afterwards, then this one would have to have a velocity of 1 in the other direction. Yeah, so it's the same as what we set up here. We'll see how the signs work out and if this was the wrong choice for the direction of that. So, same idea there. Now, the initial momentum of the system here is not 0. It's moving, right? The initial momentum is the mass of the system times 0.6 meters per second. That's 4.8 kilogram meters per second, or Newton seconds, if you like. And that means the final momentum must also be equal to that. So 4.8 is equal to the sum of the momentums after. So the momentum of this is 2 times v, plus the momentum of this. If this is the positive direction, this would have to be the negative direction. So that would be 6 times negative 3 minus v, or v minus 3, when we change the sign there. Right? So 4.8 is equal to 8v minus 18. So v is equal to, let's see, 22.8 divided by 8, I think. 2.85. All right, I sure hope that that's right. So that's the velocity of this block in that direction. So this one is now going to have a velocity of 0.15 meters per second in that direction. Right? So we actually did choose right. It's just going real slow in that direction. Okay. Now, they want to know, let me just check, make sure I'm doing the right thing here. What is the velocity of block C and the position at its center? So that we just found the velocity right there. Let's just check that and see if that's right. Oh my goodness, it is correct. That's awesome. So it's 0.15 meters per second in the negative I direction. And then it's going to do that for 2 seconds, right? Because they want to know where is it at 2.8 seconds. For the first 0.8 seconds, we already did that here. That's how far it goes. So for 2 seconds, it's going to go with a velocity of 0.15 meters per second for 2 seconds. And that's in the negative direction. So that's 0.30, negative 0.30 meters. So after the first explosion, in that 0.8 seconds, it went this far in the positive direction, and then for the next 2 seconds, it went this far in the negative direction. So the total displacement is 0.18 meters in the positive direction, or 18 centimeters. That is that's a pretty difficult problem, but good to do. I think this whole like relative velocity thing, I don't know how much we're really going to run into that. No pun intended, because it's about collisions, so like run into that. It's kind of funny. I don't think we're going to see that very much, the relative velocity business. So if that was the hardest thing about this problem, and I think it probably was, then we can just file that away. That happened, we dealt with it, and we move on. This is kind of an interesting problem here. So some athletes competing in the standing long jump use handheld weights called halters to lengthen their jumps. And we could understand that now because of conservation of momentum, right? The weights were swung up in front just before liftoff and then swung down and thrown backward during the flight. So suppose a modern 78 kilogram long jumper similarly uses two 5.5, two of them, kilogram halters, throwing them horizontally to the rear at his maximum height such that their horizontal velocity is 0 relative to the ground. So that's a lot to process there. You might want to read that again and see if you can make sense of what's happening here. So the jumper takes off, and then at the very top of her jump, she's going to throw the things backwards, but because she's already moving forward, the explosion, the separation afterwards, she's going to get a boost forward this way, and these are just going to drop straight down. So in other words, afterwards, the velocity of these will be 0 relative to the ground, and her velocity will be, it'll be increased from what it would have been. All right, so it's basically like an explosion. Oh, look at that. I was saying her, and it says his in the problem. Sorry about that. They say, let his liftoff velocity be 9.5 I plus 4j meters per second with or without the halters, and assume that he lands at the liftoff level. So what distance would the use of the halters add to his range? Okay, so I think the first thing we have to do is figure out what the range is if we don't use the halters. So we've got initial velocity that they gave us in component form of 9.5 I and 4j meters per second. So before you go any further, and hopefully it's clear to you that this is a kinematics problem. This is a projectile motion problem. Maybe it's been a little while, but hey, this is something we're supposed to know how to do. So, first we need to find the time. If we can find the time, if you have an initial vertical velocity, so here's the vertical part of this problem, of 4 meters per second, then how long are you in the air? Your acceleration would be negative g. We want to know how long you'd be in the air, and we also know, what else do we know? Delta y is going to be 0, right? It's taking off and landing at the same height. I'd like to know the time. So what is the equation that relates all of these? You could also say, because of the symmetry of such situations as this, you could also use the fact that the final velocity in the vertical direction would be negative 4. That might actually give us a little bit easier equation. Anyway, it doesn't matter which one you use. I'm going to go ahead and do that because I just thought of it. So I'm using this equation. Oh no, I'm not, because I want the time. Just kidding. That's no good. So the equation that would relate those with time would be that final velocity is equal to acceleration times time plus initial velocity. So final velocity would be equal to acceleration times time plus initial velocity. So negative 8 divided by or 8 divided by 9.8, right? After those negatives cancel out. So about 0.82 seconds we're in the air. All right, So that means, since we know our horizontal velocity is 9.5 meters per second, and now I've got my time. So how far do we go? That time times 9.5, about 7.8 meters. Right. Okay, so that's how far we go without the halters. Now we need to figure out how far we're going to go with if we eject them at the top, according to this. So at the very top of the flight, the velocity is horizontal, right? So let's see. That means that the total momentum at the top, the initial momentum of everything, is equal to the mass of everything. Now, let's see, we didn't need that for our kinematics, so I got to go back and find that stuff. 78 kilograms plus 11 kilograms of halters, so that's 89 kilograms times the velocity at the top. Think about that for a second. I think we've talked about that before. What would the velocity at the top of the flight be before we throw them? Right. It would just be the constant horizontal velocity, right? Because at the top we have the vertical velocity has gone down to 0. That's why it's the top. So there's my initial momentum of the system. The final momentum of the system must also be equal to this, because linear momentum is conserved. So that's also equal to 89 kilograms times 9.5 meters per second, whatever that is. And that's got to be equal to the momentum of the parts of the system afterwards, right? Our final momentum. So the halters are being thrown such that their horizontal velocity will be 0, right? Because they're just going to drop straight down. That means at the moment of the explosion, the velocity is 0. Then the velocity in the positive direction, that's going to increase. So we have just the mass now of the jumper, 78 kilograms, times the new and improved horizontal velocity. Right? So we can do that. 89 times 9.5 divided by 78 is about 10.8 meters per second, compared to, was 9.5 right before? 9.5 before. So what's going on here? How do we figure out how much we improved our distance? Well, the first half of the flight is going to be exactly the same, right? Up to here, the whole distance was 7.8. So half of it here would be 3.9 meters up to the peak. That's the same. But now we have a new kinematics problem to do here. Now, the vertical direction, I have an initial velocity of 0. Right? I have a, this increase is not going to affect the final velocity here, so you could still use that number if you want to. The acceleration is negative g, and I'm now, my delta y is not 0, so maybe I do have to use that, negative 4, right, because I never found the delta y to the top, so I don't particularly feel like doing that if I don't have to. So what I need to do now is find the, oh, you know what? I don't have to do any of that, do I? You know, you could do this. And you know what you're going to find for an answer? Guess what you're going to find for the time for this? It's going to be exactly half of that, right? But that makes sense because we haven't changed anything. The thing that affects the time of a flight is the vertical velocity, right? The horizontal velocity doesn't affect the time. It's the vertical velocity, the initial vertical velocity, that's going to tell you how long it's in the air. So this whole business that's happening here at the top, that's all horizontal business. It is not going to affect the time. So you could do that if you wanted to, but maybe we should have just realized it's halfway there. It's also going to be half the time on the way down because we're not giving it an extra boost up or forcing it to go down. So that time will be the same. Or, well, same for that half, right? So half of this. And now we just have to figure out, well, there's our new velocity. So the horizontal direction, I have my new velocity, 10.8 meters per second. So it's going to go that much faster for half the time. And we'll see 10.8 times 0.41. So our new second half distance is about 4.4 meters. So it's about half a meter, it looks like, so 4.4. So the improvement over 7.8 is about half a meter, about 50 centimeters. The book kept a little bit more detail in it because they have 55 centimeters. So about 50 centimeters, about half a meter. There you go. I think that's a cool problem. And last, number 45. What do we have here? 20 kilogram bodies moving through space in the direction of a positive direction of an x-axis with a speed of 200 meters per second. That's fast. When, due to an internal explosion, breaks into 3 parts. All right, so let's just say here that the total momentum at the beginning is the mass of the whole thing times its velocity. Was it 200? Yeah, 200 meters per second, which is 4,000 kilogram meters per second. So whatever happens, that's how much momentum we're going to have, right? All right, so what does happen here? One part with a mass of 10 kilograms moves away from the point of explosion with a speed of 100 meters per second in the positive y direction. It was going in the positive x direction, so that's the direction of our momentum, right? So after the collision, I've got one piece, positive y direction, 100 meters per second, and that's with a mass of 10 kilograms. And the second part, with a mass of 4 kilograms, moves in the negative x direction. This is 4 kilograms. It moves in the negative x direction with a speed of 500 meters per second. Wow. And they want to know, in unit vector notation, what's the velocity of the third part? How much energy is released in the explosion? All right, so we got some vector business to do here. So the momentum, I'm going to call this piece 1, is equal to 1,000 kilogram meters per second in the positive j direction. And this is the positive I direction, right? Our initial momentum. And then this, I have 2,000 kilogram meters per second in the negative I direction. And what I know is that the total has to still add up to this, right? So the sum of the momentums of all the pieces still has to be equal to 4,000 I kilogram meters per second. And the pieces, let's see what they have. I've got 1,000 kilogram meters per second J minus 2,000 kilogram meters per second I. And I need it to add up to this, right? So this I need to cancel. So the momentum of my third piece, I've got to get rid of all that J, right? We don't have any J here. So it's going to have to cancel that out. This is back to like our vector, our force table practicum. And then I'd like to cancel this and then get another 4,000 in the positive direction. So I'm going to have to add 6,000 to this to get back to the 4,000. You can set that up like an algebra type problem if you want, but I think the numbers were easy enough to work out there. So that's what the momentum of that final one. Sorry about my pieces being backwards there, right? I should have the I first. Let me just rewrite it like that. So 6,000 I minus 1,000 J kilogram meters per second. Okay, so what do they want to know? They want to know, in unit vector notation, what's the velocity of the third part? Well, this is the momentum, so that's the mass times velocity, right? And the mass, well, let's see, if it was 20 kilograms, this is 10, this is 4, this would have to be 6, right? So the velocity of that third piece is these things divided by 6, right? Divided by the mass. And that would give me velocity. So what is that in unit vector notation? Be 1,000 I minus, is it 167? All right, I think. J, meters per second. That would be the velocity in unit vector notation. And that looks good. Agreement with the book. And they want to know now what is the, how much energy is released in the explosion. So in other words, how much energy is lost. So initial kinetic energy is 1/2 mass times velocity squared. I'm going to do all this with my calculator in a minute. And then, excuse me, the final kinetic energy is the sum of the kinetic energies of all the pieces. And I guess to do K3, I'm going to have to find this velocity and the magnitude of that. So let me just Pythagorize that real quick before we go on. So 1,000 and 167, so square root of 1,000 squared plus 167 squared, 1,014, say. Magnitude of that, 1,014 meters per second. Okay, so let's add up the kinetic energies of the pieces. First piece, 1/2, mass was 10. Its velocity was, sorry, there it is, 100 plus 1/2. Mass of the second piece was 4 times 500 squared plus 1/2. Mass of the last piece was 6 kilograms, and we just found its velocity pretty fast. So this is an explosion, so the explosion can increase the energy, right? If you had like something just sitting and then it exploded, it would go from having no kinetic energy to lots of bits that had kinetic energy. So we might expect here that it will increase. I think that we will. So 400,000 joules. And here, I'm going to do this off screen here, so I've got so after the explosion, all that is equal to, it's about 3.6 million joules. 3.6 megajoules, if you want. So the increase is about positive 3.2 megajoules, right? This minus that. And that's the end of that assignment. Good stuff. If you're looking at this here, I'd like you to pause for a moment. Think, not pause the video, pause your shutting everything down and doing whatever else you're going to do. Take a look at this. This is how much work we want to see for a physics problem, right? So if you've got 45 and like a couple little scratchings and some, sorry, excuse for an answer. No, that sounds mean. Seriously, we need to make a very good effort, and a good effort involves writing a lot of stuff down. And a good effort also involves writing that stuff down neatly so that one can understand what one was doing when one goes back to look at it, and when one's poor, feeble physics teacher takes a look at it and tries to make sense of what's going on. So I think that's what a solution looks like, right? Okay, good night.